All right, so let's leap into section 2.3, ouch, on linear independence. All right, so let's start off with that example that I pointed out yesterday, namely that we looked at an example where we were trying to find the span of these two vectors, u1 and u2, but we found that they didn't span, and I pointed out that you can rewrite u2 as 3 times u1. So in other words, u2 was a linear combination of other vectors in the set that you were asking if they spanned R2, right? And so we noticed that this fact was captured in the sense that we got a 0 row when putting that augmented matrix into echelon form. All right, and so what that tells you is that this is actually equivalent to this guy, and that's a nonlinear combination of u1 and u2 that produces the 0 vector, right? So here, the fact that we were able to find constants that were not just zeros, so that when we formed that linear combination, we got the 0 vector back. Notice that this implies that the vector u2 is a multiple of u1. So it depends on u1, all right? And so if that happens, if we can find constants for which that's true, then there's going to be a dependence amongst the vectors that prevents them from spanning the space. And so let's extract that principle as this definition. Right, we'll say that the set of vectors u1 through um in Rn are linearly independent if the only way you can get the 0 vector by forming linear combinations of u1 through um is to choose all of these scalars to be 0. Right, so the only way you can use u1 through um to get the 0 vector is to multiply all of them by 0 and add them up. If there are non-trivial solutions like there were here to that equation, then the vectors will be called linearly dependent. Okay. All right, but notice again, this is equivalent to a system, right? The x1 through the xm are the components of the solution. These guys, the u1 through the um, will be the columns of our augmented matrix. And so basically, we're going to try to find a solution to the augmented matrix where you have, you put the components in. I'm writing this kind of symbolically, right? So you put the columns of the u guys down the left-hand side, a 0 column for the 0 vector here. And what you want to ask is, does that system have a solution other than just the 0 solution? Okay. If it does, then they're going to be linearly dependent. But I would like to actually find a way of determining, kind of a condition that would guarantee linear independence here, right? So if this happens when you put into echelon form, then linearly independent, right? That's the kind of condition I'm looking for. Just as an example, before I leap into that sort of problem, notice that these 3 vectors here are linearly dependent because you can check this out, right? So there's no way you would know that this was the case right off the bat. In fact, you'd like to be able to find a way to determine those constants in the future. But just as a example of vectors in R3 that are dependent, these guys are dependent because you can find scalars that are not all 0 for which that's true. And you can check out the arithmetic on this. Okay. Okay, so let's look at example 1. Let's ask if these are linearly independent. What we saw from here is, let's actually form the augmented matrix where the columns are these vectors, right? So those, just like with spanning, those are the columns. The right side this time is the 0 vector. Okay, and I want to solve the system. Is there a solution to this system other than x1 equals x2, x equals x3 equal to 0? If there is a solution other than that, because remember, that's always a solution. You can multiply everything by 0 and certainly you'll get the 0 vector. What we're interested in is other solutions if they exist, because if they do, that's going to imply by our definition that the vectors are linearly dependent. So to solve this, I have to put it in echelon form, our favorite. So I want a 0 there. Let's actually plug in or multiply R1 by -1, add it to R2, and plug it into R2. So I have 1, 2, 1, 0. 0, -2, 4, and 0. You can check me out on that. And 0, 3, -6, and 0. Okay, and then I want a 0 there to put this in, let's see. I want, no, I'm sorry. I want, well, actually, let's just see that. We can put in a, if I multiply R2 by 3/2 and add it, add it to R3 and put this into R3. Right, so yeah. All right, so formally I would put a 0 here and then try to put a 0 there, but I'm kind of leaping ahead because I see a dependence relationship here, right? Notice if I multiply R2 by 3/2, just so happen to notice that, and add it to R3, what you get is a row of zeros. Now, if you didn't figure that out right off the bat, you could have very well have put a, did the row combinations to get a 0 there, and then here, and you'll find the same sort of condition arising, right? Namely this. All right. And so here, again, notice you have a row of zeros. Okay. And so what does that mean? Well, this is a true statement, right? Because I'm putting a 0 on that side. So it doesn't make it false, right? It just means that you don't need that. And so notice here two things. We have these are the pivots, right? Those are pivots or leading terms, but that leaves this guy as a free variable, right? So x3 is a free variable. And in fact, from this relationship here, we note that -2x2 plus 4x3 is equal to 0. So x3, I'll take that over and divide by 4, is x2 over 2, right? So there is a dependence relationship here, right? If I chose any x2 I want, then I can find x3 from it. Or I guess I could have solved for x2, right? I said x3 was the free variable, so I can choose either one I want, but let's actually be consistent. So x2, sorry, is minus 2x3, right? So no matter what x3 I give you, I can plug that in for x2 and then go back here to find x1. Those will be constants, not all of which are 0, right? Just choose x3 not to be 0. That when you plug them in to this left-hand side, you'll still produce a solution of this system, which is the 0 vector, right? So this means that the vectors are linearly dependent. Okay. All right, so take a look here though. Again, just like before, if I don't care about what the actual dependence relationship is, then just remembering if I want to find if they're linearly independent, that happens, or they will not be linearly independent if I get a row of zeros, right? But this doesn't make a difference, right? So I don't care about that right side. I just have to remember what I'm asking, right? So a row of zeros here actually means linearly dependent, right? When the right-hand side is 0. All right. All right, let's look at another, or some observations, I should say. All right, let's make this smaller. Okay, so let's actually look at just some observations we can make from the last example. All right, so first, as long as you have the non-zero vector, right? So if you have a set containing a single vector, let's say it's 1, 2, right? So if I just gave you the set 1, 2, the set containing a the single vector 1, 2. That's not the zero vector. And so technically, if you want to ask, is this set linearly independent, there's only one vector to consider, namely 1, 2. And here we're asking, what's the only way you can get the zero? What's the only way you can get the zero vector by taking linear combinations of just that vector? Linear combinations of a single vector are just scalar multiples of that vector. And so the only way that's going to be the zero vector is if you multiply both components by 0. So x1 would have to be 0. Right? So clearly, as long as you don't have just the zero vector in here, a singleton vector that's not 0 is linearly independent. Kind of a trivial case. Next thing here, any set containing the zero vector is linearly independent, right? And so the reason for that is if you were to form a system, right, where you have your vectors, let's say u1, 0, and u2, right, you're multiplying each one by a scalar equal to the zero vector, right? And so here, that's going to produce a column of zeros. And so there are going to be infinitely many combinations of the x1 and the x3 that work to produce that dependence relationship. So you have to actually play around with that a little bit. But certainly any set that contains the zero vector itself will be linearly independent. So just play with that. Just actually show, just look at some examples. Say just for an exercise, 3, 2, and 0, 0. And then try one with 1, 2, 1, 3, 4, 1, 0, 0, 0. Right, so it'd be kind of an instructive exercise to go through that. In each case, go through and show you can find constants that are not all 0, so that when you multiply these guys by it, you get the zero vector, right? And it's pretty clear, right? Because from here, I can choose x2 to be anything I want, and it blots that guy out, right? So I could have chosen x1 equals x3 equal to 0, all right. Some of them can be 0, it's just not all. And the x2, I could be 5. It could be any non-zero number I want because I'm already multiplying it by the zero vector, right? And so that's true up here too. Just multiply the zero vector by any non-zero number, multiply each of those guys by a 0, and it'll still satisfy that linear combination equaling 0 relationship. Okay. Next one, two vectors are linearly dependent if and only if one's a scalar multiple of the other. Well, we've seen that, right? That was what motivated our definition in the first place, right? If we had 3u2 minus u1 equaling the 0 vector, remember that was the definition of linear dependence. We found two constants, not both of which are 0, for which that's true, but notice I can then solve for one in terms of the other. So this vector is a scalar multiple of that guy. All right, and then another observation is a set of vectors is linearly dependent if you can write one of the vectors as a linear combination of the others, right? And so what that means is that one of the vectors is in the span of the rest of them, right? If you can write one vector as a linear combination of the other guys, then it has to be in the span of the other guys. That's what it means to be in the span. Okay. All right, so let's look at a few more examples. Let's determine if these sets of vectors are linearly independent or dependent. All right, so if you remember, we don't care about putting in that right side of zeros in the augmented matrix. We don't care. We're just determining if there's a 0 row or not once you put an echelon form. And so let's make these guys our column vectors. 1, 1, 0, 2, 0, 3, 4, 7, 1. Okay. I'm going to put it into echelon form. So I'm going to get a 0 there by multiplying R1 by -1 adding it to R2 and plugging it into R2, right? That doesn't change the first row, but the second row becomes 0, minus 2, 3, and the third row remains the same. Okay. And similarly, I want to put a 0 there, right? And so I'm going to multiply the first one here by 3 halves. So multiply R2 by 3 halves, add it to R3, and put that into R3. So I get 1, 2, 4, 0, minus 2, 3, and 0, 0, 11 halves. Okay. Notice here, we do not have a row of zeros, right, at all. And so if I were to go through and solve this, right, this is a triangular system, upper triangular rather, we know that upper triangular systems have a unique solution, right? You can solve them. And so if I were doing this, right, if I were to put in that column of zeros every time, right, that would say 11 halves x3 is 0. Well, that means x3 is 0. Then minus 2x2 plus 3x3, but x3 is 0, right, equals 0. Well, that means x2 is 0. And then similarly, if these guys both are multiplied by 0, x1 has to be 0. And so in this case, the vectors are linearly independent, right? Because the only solution you got was the 0 solution. The only constants you could multiply these 3 vectors by, so that when you add them up and you get the 0 vector, is zeros themselves. Okay. And then notice here that those are your pivots. So every column has a pivot, every row has a pivot. Okay. So if you were asking about the span, right, so 2 different questions. Linearly independent, because this system, if you put zeros here, had the solution just of the 0 vector itself. So there were no 0 rows, and every column had a pivot. If you were putting an A, B, and C in here and asking what was the span of these 3 vectors, in other words, for what vectors A, B, and C is there a unique solution, you'd say all of them, because it's upper triangular, and there's an A, for any A, B, and C you give me here, there's going to be a unique solution down here, right? So it seems to all be depending or pivoting on the pivots and whether or not they exist in the row or the columns, right? So let's actually see how exactly in the next example. So I have a set of 3 vectors in R4. I'm going to make those again my columns. Oops, 22. And I want to put it in echelon form, right? So again, I got to put zeros here, right? So let's add R1 plus R2 and clunk it into R2. Let's multiply R1 times -4, add it to R3, and multiply R1 by -5 and add it to R4. All right, if I do that, what I get is this matrix 1, 4, 1, 0, 7, -7, 0, -18, +18, 0, -17, +17. Okay. And then if I were to, let's see here, -17. Okay, now notice these 2 rows here, all of the rows have 1 negative and 1 positive of the same exact number. And so what that tells you is I can multiply R2 by the correct constants each time, so that when I add it to R2 and or when I add it to R3 and R4, I'll get the 0 vector, right? So in other words, for example, if I multiplied row 2 by 18/7 and added it to R3, I'll get the 0 vector, the 0 row. And if I multiplied R2 by 17/7 and added it to R4, I'll get the 0 row, right? And so what I get here, I'll have to squeeze it in, the first 2 rows remain unchanged, but I get 2 rows of zeros by having done this, right? Notice that our pivots in this case, we have a pivot is the leading term in each row. And so I have those guys. All right. I have no pivot in column 3. So there is no more, there are no more leading terms because each of the other rows has a 0 everywhere. So this column has no pivot. And you have 2 0 rows. And so we know that these vectors are linearly dependent. Okay. And they're not going to span R4, right? First off, you have fewer vectors than you have dimension of R4. But moreover, you're going to have conditions on the C and D at least over here, right? Or whatever, not even C and D, whatever these constants turn out to be after having done these row operations, you'll have conditions on A through D imposed by these 0 left-hand sides to make it work. And so they don't span R4 either. Okay. All right. So the key observation here, what I want to do is boil down to just looking at when and where the pivots exist and where they don't, right? And so the columns, so remember, we take these vectors and we make them the columns of our matrix. So the columns will span Rn if and only if the echelon form doesn't have a 0 row, right? So if there's no 0 row, that means that the system will have a solution. All right. But if you're not going to have a 0 row, that means that every row contains a pivot, right? Because every row has to have a non-zero number, and so every row is going to have a pivot. You can't, as a result, right? You'll say, well, what about this? If I had 1, 2, 1, 0, 0, 1, 1, 0, 0, 1, and 0, 0, 2, right? Suppose I did that, right? Well, this row doesn't have a pivot because I can get rid of it by multiplying this guy by -2 and adding it, right? So you'd have a 0 row here, right? So by saying that every row has a pivot negates the fact that you have a 0 row, right? So it's kind of a way of rephrasing only in terms of pivots. All right. And then we'll say that these vectors, again, are linearly independent if and only if there are no free variables. And so every column has to have a pivot, right? And so if you looked at the last example, right, if you looked at this example here, this column 3 didn't have a pivot, right? There is no leading term in the third row to give it a pivot. And so the fact that it doesn't have a pivot produced this free variable. All right. And so if there's a free variable, that means that those two vectors that correspond to those coefficients are linear combination or scalar multiples of each other. And so they're dependent. And so if you have a column that doesn't have a pivot, right, then you're going to have a free variable, and those vectors then will be linear combinations of each other. All right. If you take those two together, we know that if you have the same number of vectors as you do the n in Rn, then those vectors will span Rn if and only if they're linear independent, right? There's no, in other words, you're just looking for 0 rows in that case, right? If there's n, if the n and the m are the same, right? So if you don't have more rows than columns or more columns than rows, then the only way they can span is if they're linearly independent. All right. Let's take a look at just a practical example. Suppose you have protein, fat, and carb in grams of 4 particular supplements, and the components here, right? So the protein, the fat, and the carb are the X, the Y, and the Z, the first, the second, and the third components each time around. And we want to know if they're linearly independent. All right. So linear independence again means I'm going to write down, the vectors A, B, C, D as column vectors. And I want to see if there is a pivot in every column, right? That's the question, right? For linear independence, is if there's a pivot in every column, that means that they are linearly independent. So let's put this into echelon form, right? So I want to get, and first, before I do that, notice that it'll be easier if I plug in, if I make this row 1, because then I don't worry about multiplying the 8 by fractions to kill off the other rows. So the first thing I'm going to do is interchange row 1 and row 2. If at all possible you want a 1 in the as a leading term of the first row, because everything starts off there. Okay, now I'm going to multiply the first row by negative r, or by negative 8, add it to R2, and put it into R2. And then the same way, I'm going to multiply R1 by negative 4 and add it to R3. Okay, if I do that, the first row doesn't change. I get 0, minus 5, 9, 1, 0, minus 6, 2, negative 1. Okay, and then I want to put a 0 here, right, again, to put into echelon form. And so I'm going to multiply R2 by negative 6/5, so that when I add it to R3, it kills off that negative 6. All right, and so the matrix that I get as a result looks like this. You can check the arithmetic as usual. Okay, I'm going to now identify the pivots, right? So I have this guy, and this guy. All right, this column, notice that columns 1, 2, and 3 have pivots. Column 4 does not. So no pivot in column 4. And so that means the vectors A, B, C, and D are linearly dependent. All right. And so you can build, so in other words here, notice that would be a free sort of variable, right? And so for example, if I were writing x1 times A plus x2 times B plus x3 times C, and that's equal to 0, then I could actually choose anything I want for x4. In fact, I'll choose x4 to not be 0, and then I can rewrite the vector that corresponds here as a linear combination of these guys, right? It's 1 over x4 times the, move all the other guys over. All right. So, I mean, I'm not actually finding the actual constants, but what this implies is that I can rewrite D in terms of the others, which means I don't need all 4 supplements. You can get everything you need from these 3, right? So, no. Okay. Kind of an interesting sort of question for anyone that's out there that takes different supplements, right? You can determine which ones you need from the others so you can save money. All right. So now we have this. So notice there, oops, sorry. Yeah, I keep doing that. All right, in the previous example, we had more columns than we did rows. And so if you have more columns than you do rows, it's impossible for every column to have a pivot, right? There's only so much you can go down when you're doing echelon form. So if you have more columns than rows, the very last row is going to have more than, it's either going to be a 0 row, which is not going to help you, or you're going to have 2 variables, 2 non-zero entries at least, in which case you're still not going to have a column with a pivot, right? And so that's what this is saying here, is if you have more columns than rows, you can't possibly be linearly independent, okay? In other words, if you have 4 vectors in R3, one has to depend on the other 3. It has no choice in the matter. If, however, you're just given 3 vectors in R3 or 2 vectors in R3, There's no way to determine if they're independent just by looking at them. You have to actually do something. The only definitive one you have is if there are more vectors in your set than there are dimension of the space, right? So if you have R5, if I gave you 7 vectors and asked if they were linearly independent, you'd immediately say no, because there are more vectors than there is the span of the dimension of the space. Okay, if n and m are equal, then in fact these are the same exact thing. So they mean the same thing, right? So the columns, the vectors that you're starting off with in your set, they'll span Rn and they'll be linear independent. They mean the same thing. So when I say they're equivalent, that means logically spanning is the same thing as linear independence. And it's also the same thing as this, because this is asking, remember, this is the same thing as saying for what vectors B are in the span of the vectors you're starting with, right? So remember, the way you form A is by taking your vectors and making them columns, right? If we form an augmented matrix where we have those columns as a matrix and the right side being B, if you ask the question, for what do those vectors be, does this system have a solution, right? You're asking whether or not if that vector B is in the span of those columns. But that's equivalent, if you remember our more compact notation, that's equivalent to saying that this guy has a unique solution no matter what B you give me. All right, so these mean exactly the same thing. All right, so let's actually go through this problem kind of from beginning to end to kind of pull everything together. All right, so you have a matrix A and a vector B, and you want to describe the solution set of this system, right? So let's form the augmented matrix by using A on the left and then B on the right. All right. Same thing. I want to get this into echelon form. And so I want zeros here and there. So I'm going to multiply R1 by -2 and add it to R2, put that into R2. And then I'm just going to add R1 and R3 and put that into R3. If I do that, the top row remains unchanged. The next row becomes 0, 0, 1, -4, -5. You can check the arithmetic on this. And -2, 8, 10. All right. Still not done, right? Because remember, each row has to have successively more initial zeros than the other. So I'm going to get rid of this guy by multiplying R2 by 2 and adding it to R3 and then putting that into R3. All right, so if I do that, the first 2 rows aren't going to change. But the last row becomes a 0, 0, 0, 0 row. Right, so all zeros here. All right. And so what that means, we know they're going to be solutions because that's not a false statement, right? If this had been false, then that would mean that this vector here was not in the span of those guys, and we'd be done with that. But it is not false, right? In fact, we're going to get infinitely many solutions, right? So the pivots are here, right? So those guys are the pivots. And so what I'm going to have to do, I'm going to make x4 free. So let's call x4 a free variable. I'll know that, I'll know this, I'll know this. X2 is also going to be free. And remember, the way I do this, I decide which ones are free, and then I label them in increasing order of the subscripts in the same manner here, right? It's just matter of preference. Okay, so x2 is free, x4 is free. Let's find x3, right? So x3 minus 4x4 is -5. But remember, x4 is s2. And so if I take this term to the right, I get 4s2 minus 5. Okay. There's my x3. And now I'll plug all of these guys up here to get x1. x1 minus 3x2, x2 was s1, okay, minus x3, so minus 4s2 minus 5, plus 6x4, but x4 is s2, and that's supposed to be 6. All right, so now if I simplify this, I have a 3s1 negative, take it to the right, minus 4s2 plus 6x2 is 2s2, subtract 2s2 from the right, and then positive 5, subtract that from 6 to get plus 1. All right, and so those are the solutions I have. And so what I'm going to do now is I'm going to rewrite this, okay, as a set of, or as in vector form. So I'm going to pull the S1 out of each of them, right? So I'm going to write each of these as a number times S1. That number might be 0. A number times S2, and then whatever remains as the constant vector. So for the first component, I have a 3 here, a minus 2 there, and a 1. That's for x1. For x2, I just have an s1. I don't have a constant or an s2. For x3, I have a 4 on the s2 and a minus 5, a 0 there. And an x4, I just have an s2. Okay, and so this, and here remember s1 and s2 belong to R. All right, and so this is the set of solutions. All right, so the solution set of this equation is that, right? So it has infinitely many solutions. Good. Okay, the next one, are the columns of A linearly independent? Well, remember from our statement, we have columns are the vectors in a set. So these vectors, these column vectors are linearly independent if once you put an echelon form, every column has a pivot. Well, every column does not have a pivot. There's no pivot in columns 2 or 4, right? Because the only pivots I have are the red box guys. So the answer to that is no. Columns 2 and 4 have no pivot. Okay. And finally, remember here, do the columns span R3? So remember, we're not looking at this right side. We're looking for a general A, B, and C. And so had I replaced that right-hand side by A, B, C, that would mean that the fact that I had zeros here, that would impose conditions on the components of that arbitrary vector to be able to make sure the system had a solution. And so the minute you have conditions like that, we know that they don't span. And so the 0 row above, so this part here implies they do not span R3. Okay. And then the question here, is there a B for which this guy has no solution? Sure. All you have to do is start up here in such a way that would produce a non-zero number there, right? And so, for example, so the last one here is yes. You just have to tweak that and you can tinker with it. But if I just change this last guy here just a little bit, going through these row operations will put a non-zero number there. And that would mean that that system didn't have a solution. Okay. All right. And then finally, find the vectors that span the solution set of this guy. Well, here, that would mean I put zeros on the right-hand side, right? And so if I put zeros down on the right-hand side, that's just going to tinker with this, right? But it's pretty easy to see that all you'd have to do is consider this part, right? Because if this wasn't here, if you multiply those by any S1 and S2, that's going to contain the origin, and it won't account for that extra constant term. So what I'll do here is I'll say, show that if I only took these two vectors, So they're the ones that are attached to the free variables. This spans the solution set of the homogeneous matrix equation, right? And to do that, i.e., what does that mean? It means to go through and okay, so what is it? I'll leave it alone. I don't want to tell you too much with that. So in other words, go through the same sort of thing here, but then show that you can rewrite every solution of this guy. So solve this system and then show that you could write every one of those solutions of the system as linear combinations of those guys. Right? So you're not trying to determine a span, you're trying to say, I'm going to solve this system by replacing the right side by 0, 0, 0. And then once you have all those solutions, show that you can rewrite them as linear combinations of those guys. All right, so try that. Okay. Good. All right, and I think that ends the discussion for section 2.3. Sorry about that. All right, so give linear independence a go, right? There are a couple things that to keep in mind, but it all relates to the pivots and the 0 rows. It's very easy to confuse them. So when you're working through the exercises, keep kind of a summary sheet there that lets you know what it means for the vectors to be linearly independent and what it means for them to span the space if they happen to not be square matrices. If they're square matrices, they mean the same thing. All right, give it a go and let me know what questions you have. All right, take it easy.